Hello, I'm Helen Qin from Thomas Jefferson High School for Science and Technology. Nice to meet you. This is my project that I will be presenting today, From Imperfect Teachers to Robust Students, Targeted Role Model Augmented Distillation for Energy Efficient Edge AI Traffic Light Detection. So this work was advised by Dr. Yuan at Rochester Institute of Technology. And the question we will investigate today is when a large teacher model has a blind spot, can a much smaller student model avoid inheriting it? Autonomous vehicles motivated me to start this project. Traffic light detection is a critical component of road safety systems. And when I was learning how to drive, I saw that the yellow light signal can make one driver slow down but another one speed up. The yellow light shines only about 2.5 to 10% of a traffic signal cycle. So yellow lights are scarce in real-world datasets, however, they account for a significant portion of accidents at intersections. So when drivers must make a split-second decision, a warning device must recognize the signal state quickly and run locally without the cloud. And the conclusion we draw from this is that yellow lights are a rare event, but they are critical to driving safety. Large AI vision models can be used for traffic light detection, but before they can be used for commercial use, there are three challenges. First, capable models are often too energy intensive and expensive to be used in everyday safety systems. Second, railroad datasets are imbalanced, so yellow light recall rates are low even for large AI models. And third, when large models are conventionally distilled for edge deployment, they pass down similar or worse blind spots to their student models. These student models often fail to detect rare but critical events. So now we want to determine a method for creating a small student model with increased rare event performance and no significant decrease in overall performance. The Bosch Small Traffic Lights dataset is an open source dataset used for AI vision model training. This dataset has 9 classes: red, green, yellow lights, off, and 5 arrow classes. I only use the 3 main states, and you can see here the data distribution and the number of images classified. The majority were red and green, with only 577 that were yellow instances. So this is just about 0.82% of this evaluated in the 3 state count. So this is a flowchart of my proposed framework, the overview of the targeted world model augmented distillation. So first, the teacher model is trained on the real-world Bosch dataset. Second, we're going to use the world model to generate synthetic data that oversamples the rare event. And then third, to use the teacher model to pseudo-label and filter the synthetic dataset. And fourth, mix the filtered synthetic samples with the real dataset samples at controlled ratios and then train the student. So finally, evaluate the student model using real-world testing data. The key guardrail in this situation is that the synthetic images enter the training dataset only. So they never enter validation or testing stages. The standard pre-trained yellow model recognizes a traffic light as an object, but our task requires state-specific labels. That is the red, yellow, and green lights. So you can see some examples down here where yellow gives the bounding box and a confidence level for the label, but it just says that it is a traffic light. Okay, so now on to what we're going to be using to simulate the synthetic data. So Carla is an open source driving simulator, and in this project, Carla serves as the road model with a controllable driving environment for road geometry, traffic behavior, lighting, weather, and a simulated front camera. Carla allows the user to generate thousands of synthetic images with the user's customization. So, unlike generic augmentation, this generation for this project is targeted towards yellow lights with random factors such as weather, time of day, distance, traffic, and background to add variety to the data set. Okay, so here are some examples um, of how the color program can be used to change illumination, traffic density, and viewpoint. You can also see that the um, simulator is collecting images. These images do not need to be indistinguishable from photographs, so their purpose is increasing the training set's coverage of the rare event under varied conditions. I used the teacher model to then pseudo label the synthetic data set and filtered the pseudo labeled synthetic data images for images labeled above a certain confidence threshold. And with this, we ask the question of whether a model's learned ability of synthetic yellow light detection can be transferred to real world yellow light detection. Okay, now here are some examples of color generated scenes with yellow teacher pseudo labels. In the top left, we see this is daylight with normal weather. And then in the top right, we can see heavy rain, while in the bottom right, it is sort of near dusk. The teacher model has been trained to recognize the traffic light colors. So the teacher model labels the traffic light um, in red, yellow, and green. You can see in these three photos. Okay, now this slide shows the targeted generation formally, sort of in mathematical or theoretical form. The signal state is the variable we deliberately bias, and then the environment variables randomize weather, illumination, distance, traffic clutter, and camera viewpoint. So it's for domain randomization. Okay, so next, the yellow 11 teacher model pseudo labels the color frames. We retain detections above a threshold of 2 over 9 confidence level. This is twice the random chance baseline for 9 classes. And the threshold is intentionally looser because the teacher struggles to detect yellow light events already by itself. So a stricter filter would recreate the scarcity we're trying to fix. The trade off, however, is label noise, which is roughly bounded by the teacher's 80.5% yellow light precision rate. And Carla's ground truth labels are an important future addition, but for now, teacher filtering can act as a domain filter and keep the workflow applicable to generative world models without ground truths. The training distribution is a mixture of real Bosch data and teacher labeled synthetic data. I tested 7 real to synthetic ratios, and at the largest injection, the three main signal states became balanced in the dataset, which was 2 to 1, and the loss remains the yellow multitask objective. The two variables we study are the injection ratio and the classification loss weight. I capped injection at 1/3 so simulation data would not dominate the training distribution. This slide is to illustrate our experimental guardrail. The color data injection appeared only in the training mixture, so the model selection uses a validation set made entirely of real Bosch images, and the test split is also entirely real and held out for reporting. A student model that learns simulator artifacts should therefore lose on the real validation set rather than being rewarded for fitting it into the synthetic data. So Formula 1 is the recall formula for the dataset and the class subset. This calculates how good the model is at correctly spotting specific groups of items. For example, the rare event, and it measures the percentage of target items the model correctly identified out of all the target items actually present. And then Formula 2 is the majority regime tolerance set. This creates a short list of acceptable settings for a student model. Then to make the cut, the student model must perform well on rare, hard to find items without falling too far behind how well the baseline teacher model performs. And then Formula 3, which allows us to pick the winner as the highest rare regime recall candidate selection. From the list of student models with acceptable settings, the student with the best configuration is selected. That has the highest performance on the rare event. So I collected a small US data set of railroad traffic lights, similar to the Bosch data set in Virginia, Fairfax County of the United States. And roughly 1,000 photographs were taken and labeled. The final annotated evaluation set was 274 images with 517 traffic light instances, including about a um, even distribution of the three traffic light states with a bit more yellow lights. None of these images were used for training, validation, or model selection. They were instead used for testing data because the set is small and single location. This is served as a pilot test for the proof of concept. These three surfaces, show our optimization results. Red recall stays in the upper 90s, and green recall stays in the lower 90s across all of the 35 student models. So the 5 point tolerance is generally satisfied. Yellow light recall is sensitive to the targeted injection and reached a peak of about 69% at the 80 to 20 Bosch to Carlo mix with a classification weight of 1.5. And on the heat map, you can see it is the most yellow color. So Bosch only student configurations range from 43.7 to 50.7%, which was close to the teacher's 50%, as predicted that these student models inherited the teacher model's blind spots. And the plotted variation was across the classification weight settings. These bar charts summarize precision and recall across injection ratios. The central pattern is that targeted injection raises yellow light recall, while red and green remain near the teacher on the in-domain Bosch evaluation. And also, you can distinguish the average injection ratio from the single selected configuration, which is the 69% recall on the best student model that is 80 to 20 real to synthetic ratio with a classification weight of 1.5. These confusion matrices can further illustrate the error patterns. The teacher matrix on the left shows true yellow instances that were missed as part of the background, and the selected student matrix on the right shows that the corresponding yellow recall pattern on its Bosch uh, evaluation is much higher. So for the quantitative comparison, you can use the normalized recall values of 50% for the teacher and 69% for the selected student. And the road model distillation method corrected the yellow light blind spot much higher for the student model. There is a 19% increase in recall between the teacher and student model without significant decrease in yellow or green light recall. And the selected student model size and performance makes it much more suitable for edge deployment. And also, the p value was statistically significant. The next question is whether or not the rare event increase survives in a change of domain. So, after evaluation on the real world data set that was collected in Fairfax County, I found that the absolute yellow light recall on the Fairfax zero shot data set was 10% for the teacher and only 1.5 to 5.6% for the non injected students, but it was as high as 48% for the injected distilled models. So finally, for edge deployment, a Raspberry Pi 5, an AI chip, a camera, and a speaker, and a portable power bank was used to demonstrate that engineering feasibility, and it supports the edge AI motivation. And you can see there are some photos of the device along with attached to the car on the road. So the most important contribution was the student model selection framework that allowed us to evaluate which synthetic to real world data injection ratio would be the best for student model performance. However, the limits of this experiment are also equally important because only one rare event case and one detection task was studied. And additionally, Carlaw also leads a simulation to railroad data gap, and the zero shot set for validation was small. So these are for the future works. So, in conclusion, it is demonstrated that a targeted road model augmented distillation method can meaningfully improve the performance of student AI models to surpass teacher AI models and it is able to better handle rare event cases. And there was a 38% rate in recall. And this is a scalable strategy to address data scarcity and correct blind spots in models. And then it demonstrates an innovative approach to building robust, rare event resilient, edge deployable AI model systems. So this is both energy efficient and more accurate. Okay, thank you for listening, and please feel free to contact me for any questions. And there's my email on the screen.